All right, so for this example, section 10.1, area under the curve, we've just been talking about how the fact that if you have a function that represents an upper boundary to an area, so this function right here, y equals x squared plus 2, in this particular question is the upper boundary of this area. Now we can take an approximation. We can take an approximation of this area using the trapezoid formula method, right? So remember the area for a trapezoid? And why would we want to know that? Well, this is the area for a trapezoid formula. And if you look sideways here, you see how I actually could maybe take this point and draw a trapezoid, you know, if I put a straight line there. Now it's not a straight line, it's a curved line because it's a parabola, but we could have a little bit of a guess, and this would be a bit of an overestimation of what the actual area would be, but we would have a ballpark, right? So could we do that real quick? What is the what's the length here between 0 and the graph at x equals 2? So when x equals 2, what is y? Okay, when x equals 2, what is y? 2 squared plus 2? 6? Okay, does that sound right? X equals 2? 2 squared plus 2. That's 6. Okay. What is b here? What is this length over here? You put in 4, what do you get? 18. Okay. And what's the height? Well, the height would be, if this trapezoid, again, the trapezoid is on its side, right? This is what we're doing. Something like this. Right? That's the trapezoid tipped over. So between 2 and 4 here is 2 units, right? Okay, so what's the area here? Well, 1/2 times 2, that cancels each other out. 6 plus 18 is what? About 24 units. Okay, 24 units. That's our ballpark guess, just to begin with, not using calculus, not doing anything. Let's now go to this graph right here. Now, what I've done is I've kind of copied and pasted a little picture from Desmos, and this is the graph y equals x squared plus 2 right here. So here is x equals 2 down here, and here's x equals 4. And so if each of these unit is 1 square unit, which that's 1 by 1, so if that's a square unit, we could literally count up the number of units and make another estimation just by counting this way. So I've got all the whole number units mentioned here, okay? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Those are all the whole units. Now if we add up the pieces, so this one right here, and another little piece maybe somewhere up here, that would be 18. Okay, so this piece going with maybe something like this piece would be 19. This one with this one, maybe about 20. We've got this one, and now this one here looks like that's about 21.5 or so, and then just not quite 1, so maybe 22.2-ish, I don't know. Does that make sense, what I'm doing? Just adding up fractions of the squares here? Okay, so how does that compare with what we just did? Oh, 24 and 22, okay. So let's see. Now we're going to do the calculus just to decide, or to figure out if we can find out what the exact value is, okay? And so what we did was what we just learned here in class, is that if we take the antiderivative of the upper function evaluated at the right endpoint of the area that we're looking for, and we subtract from that the antiderivative of the upper boundary function evaluated at the lower endpoint, okay, of the area we're trying to find, that should be the exact representation of the area. So what we need to do first of all is we need to find the antiderivative of this, y equals x squared plus 2. Can we do that? Yeah, we sure can. Okay, so let's say that's going to be capital A, all right? So what is the antiderivative of x squared? Remember what we do is we add 1 here, that's going to be x cubed, and then what do I do? 1 over 3. Very good. Okay? Now if I have just a constant, the particular antiderivative would be 2 what? 2x, okay? Because again, the derivative of 2x is 2. Now we could do plus c, okay? We could do plus c, and I guess maybe we will. Let's do plus c, because we don't know if there's another constant involved here. And so this is the area function, okay? So if I follow my rules here, like what we set up here, the area underneath the curve, what I need to do is I basically need to do this function right here evaluated at, this is a notation that maybe you're not aware of yet, but evaluated at 4, and then subtract the value at 2. So this is between 2 and 4 here. And again, I don't know if you've seen this notation yet, probably not. So let's do it over here. That's going to be 1/3. We're going to do 4 cubed plus 2 times 4. And you can put the plus c in there. We'll see how that all works out. And let's do evaluated now at 2. Okay. Okay, so what's 4 cubed? 64 over 3 plus 8 plus c minus, this is 8 over 3 plus 4 plus c. Okay, so if we figure this out here, evaluate this, then the c's are gone. You see that? C minus c, so those are gone. 64 minus 8 over 3 is what? 56 over 3. 8 minus 4 is plus 4. So this is 4 is going to be actually 12 over 3. So what do we have? 68 over 3. Am I doing my mental math correctly here, do you figure? 60, sorry.
What is it? The 12 over 3?
4. 12 over 3, that's 4.
Oh.
4 is the same as 12 over 3. I'm just trying to get common denominator.
Where did you get 56 over 3?
64 minus 8. All right, so 68 over 3. Now, we guessed an overestimate of 24, an underestimate of 22.2 maybe. What is this? 68 divided by 3. Oh my goodness. 22.67, right? 22.7. So, isn't that amazing? So it seems like our estimations match up with what the calculus is saying that we should have. So this is, like I say, the area is about 22.7 units squared. Okay? So there's an example of using antiderivatives to find areas under a curve that is super important for the beginning of, this is integration, so the integral calculus, we're starting to find out what the applications of integrals are.